Friends, welcome to the tutorial series on network analysis made simple. During the previous tutorial on review of differential equations, we have learned to identify the type and the order of ODEs. We also have learned to differentiate between the homogeneous and non-homogeneous differential equations. Further, for few electrical networks, we wrote the system equations and learned to bring them to what we called as a standard form of ODE. In this tutorial titled Classical Approach to Transient Analysis, we shall discuss regarding the transients in electrical networks. Friends, do you know that the transient analysis is as important as steady state analysis? Therefore, it is necessary to discuss the causes and effects, merits and demerits in detail. We know that the mathematical models of electrical circuits turn out to be differential or integral differential equations. Also, we know that the solution of ODEs using pure mathematical approach is a tedious task. So, to make the solution simple, a classical approach is made easy using our knowledge domain of electrical networks and network elements. And this is the central idea of this tutorial. I am sure you will enjoy it. Friends, do you know what is a transient? In my opinion, transient is a phenomenon which occurs knowingly or unknowingly in all physical system operations, including human beings. Are you surprised? Yes, friends, transients do occur even in human being. For example, consider an ECG waveform recorded for a human being as shown in figure. The first part is the ECG when a person's activities are normal. The second part of the waveform is his ECG when he is experiencing a severe heart attack or heart arrest. The third waveform shows the final state. Hope you know what it is. Friends, he is dead. Similarly, transients occur in machines and in electrical networks too. Consider the waveform of current drawn by a DC motor when it is started at t is equal to 0 by applying the supply. During the first state, the motor is at rest, current drawn is 0. After the power supply is switched at t is equal to 0, you see that the current drawn increases suddenly and it takes some time to decrease during the transient state. After some time, the motor draws normal no load or load current as the case may be. Observe that the normal current drawn remains constant. Next, consider the transient in induction motor starting. Here also, you see that the starting current increases enormously and take some time to reach normal state as seen. Observe that during transient state, current changes are non-periodical. But during steady state, the current varies periodically. So friends, we can define a transient as a transit state from one steady state to another steady state. Observe that this happens in all the examples that we have described. So, it also may be stated that the transient state is a temporary state. It vanishes with time, produces non-periodic variations, and magnitudes of non-periodic variations will be many times more than the normal values. Because of these reasons, friends, transient variations may cause disastrous effect when they occur. Friends, now let us see when and why transients appear in electrical networks. In the first place, transients may appear due to switching. Switching could be manual or due to the operation of protecting devices or due to the shape of the supply waveforms such as clock signals, for example. Transients may also appear due to unforeseen reasons such as faults and short circuits. When faults occur or when system is overloaded, the protecting devices operate and disconnect the supply. Under such circumstances also, transients may appear and produce large variations of voltages and currents. Then, you may be thinking, which property of circuit elements produce transients? Friends, you know that inductance and capacitance store energy in them. The voltage across inductance VL is equal to L into di by dt or L is equal to VL divided by di by dt. What does this mean? Friends, inductance is a property of a circuit element which opposes the change in current. Observe the equation for L. You see that di by dt appears in the denominator, and that is the reason. Further, you also know that energy stored in inductance EL is equal to half Li square, and this energy is stored in the form of electromagnetic field in the inductance. Similarly, current through the capacitance IC is equal to C into dV by dt or C is equal to IC divided by dV by dt. What does this mean again? Friends, capacitance is a property of a circuit element which will oppose the change in voltage across it. You see that dV by dt is appearing at the denominator in the equation of capacitance. This energy is stored in the form of electrostatic field in the capacitance element. So friends, it is interesting to note that these energy storing elements, inductance and capacitance, are responsible for the characterization of the entire electrical network. Do you know? Friends, an electrical network as a physical system is characterized by certain energy conditions in its operation both in steady state and during transients. Friends, now it is a time to distinguish the process of energy transfer in transients. One thing you know, during steady state, the variations of voltages and currents remain constant in DC circuits, whereas in AC circuits, they vary periodically. That is what we say parameters in the steady state are time invariant. Then, what will happen to energy component? Friends, during steady state, energy stored in inductance and capacitance elements are supplied by DC sources in DC circuits, whereas the energy in AC circuits is changed periodically or transferred between inductance and capacitance elements. But friends, remember, energy transfer or energy distribution during transient cannot happen instantly or abruptly because you know that the change in magnetic energy requires change in current, but inductance will oppose the change in current. Similarly, change in electrical energy requires change in voltage and the capacitance element will oppose the change in voltage. That is exactly the reason why the change in voltage and currents take some time to reach the steady state values during transients. Of course, this time could be very small in terms of milli or microseconds, but magnitudes of voltages and currents during transients might be so large to cause damage to the system. Hope it is clear to you all. Friends, from the earlier discussion, we have clearly understood regarding transients, how they appear, what circuit elements produce transients, and so on. Friends, if I ask you, are transients desirable? What is your answer? Friends, My answer is both yes and no. No, because in large power systems, the transient voltages and currents are so large in magnitude so as to damage the equipment itself and bring in instability in the system operation. Further, large amplitudes may cause interference to the adjacent networks. Also, they may increase the thermal distortion and also increase the electromagnetic stresses on the system. But in contrast, friends, you know that all electronic systems work on digital signal, and that digital signal is a clock. And you know, clock is a signal which is switched from 0 to 1 and 1 to 0 at every half cycle. Also, you know, most of the electronic systems contain energy storing elements. Therefore, transients are produced in every electronic system. But for their safe working, these transients are controlled and systems are designed to overcome the transient effects in electronic systems. Friends, next I will take you to another interesting area of transient analysis. Different approaches are available. Broadly, the approaches can be classified under two headings. One is a transform approach and the other is made easy classical approach. We shall learn these aspects in our next discussion. Friends, first let us take a transform approach of solving ODE. Two approaches are available. One is Fourier transform approach and the other is Laplace transform approach. First consider Fourier transform approach. In this method, the differential operators are transformed into multiplication operators. In many cases, this allows us to eliminate the derivatives of one of the independent variables. The resulting problem will be easier to solve. Fine. But to recover the solution in terms of original variables, an inverse transform is needed. Friends, this is typically the most laborious intensive task and it demands deeper mathematical knowledge. Next, consider a Laplace transform approach. We know that the Laplace transforms convert the differential equation into an algebraic equation. In the process, the differential equation which is in the time domain is transformed into a frequency domain. Of course, solving a converted algebraic equation is much simpler than solving a differential equation. Fine. But to obtain the solution in the time domain, you know, an inverse Laplace transform is to be used. This also is the most laborious intensive task, friends, and it also demands deeper mathematical knowledge. Therefore, you remember I said a classical approach is a made easy approach. So, let us see what prerequisite is required to use classical approach to solve ODE. First, we need the knowledge of formation of differential or integral differential equation for the given circuit. Next, we need the basic mathematical knowledge of rearranging the obtained equation and bringing it to what we called it as a standard form of ODE. Of course, these two steps are common and are needed for transform approaches also. Friends, listen carefully. Here onwards, you find the difference in using a classical approach. To use classical approach, you need only basic knowledge of simple differentiation and integration rather than the deeper knowledge of mathematics. Of course, we need basic knowledge of finding initial current through the inductance and initial voltage across the capacitance before switching. This process is very simple, friends. So friends, consider the classical approach to transient analysis. This method is based on determination of differential equation of the given circuit as usual and obtaining the solution into two parts. One part is a natural solution and the other is a complementary solution. Of course, The classical method of solution is also fairly complicated mathematically, but it is made simple by using the knowledge domain of electrical networks and the characterization of network elements. I will tell you how simple it is. Friends, to keep you in the comfortable zone to understand the procedure of solving first order ODE, I prefer to take you along by taking a simple example of a series RL circuit connected across a DC source through a switch K as shown in figure. After the switch K is closed, writing the equation for the system response, we get R into I plus L into di by dt is equal to V. By dividing throughout by L and rearranging it, we get di by dt plus R by L into I is equal to V by L. You know, this equation is an ordinary linear first order non-homogeneous differential equation with constant coefficients. This equation can be written into a standard form of ODE as di by dt plus P into I is equal to Q, where P is equal to R by L and Q is equal to V by L. We see that in this equation, P is a constant which is derived from the values of the circuit elements R and L, and Q could be a constant in DC circuits as it is now, or it could be a function of time as in AC circuits. Now, let us proceed to develop procedure to solve this first order ODE using classical approach. Consider the standard form of a first order ODE di by dt plus P into I is equal to Q. Let it be equation 1. We know that a more general method of solving ODE is to multiply both sides by a so-called integrating factor so that each side becomes an exact differential. Let us see how to proceed to obtain the solution in our next discussion. Friends, you see that the first order ODE equation 1 is reproduced here for convenience. Let us use an integrating factor e to the power of pt, where p is the same constant as obtained earlier. By multiplying on both sides by an integrating factor e to the power of pt, we get e to the power of pt into di by dt plus e to the power of pt into p into I is equal to q into e to the power of pt. Let it be equation 2. We know that d by dt of x into y is equal to y into dx by dt plus x into dy by dt. This is a simple differential rule. In our equation 2, let x is equal to I and y is equal to e to the power of pt. With these substitutions in mind, if we observe the left hand side of equation 2, in which we find e to the power of pt is y, di by dt is dx by dt plus I is x, and e to the power of pt into p is dy by dt. So, you see that the left hand side of equation 2 is equal to d by dt of I into e to the power of pt. In view of this, we can write equation 2 as d by dt of I into e to the power of pt equal to q into e to the power of pt. Let it be equation 3. By integrating on both sides, we get I into e to the power of pt is equal to q into integration of e to the power of pt into dt plus k, where k is constant of integration and is the initial condition. So, by taking e to the power of pt onto the right hand side of equal to sign, we get I of t is equal to e to the power of minus pt into q into integration of e to the power of pt into dt plus k into e to the power of minus pt. Let it be equation 4. Are we happy that you have already got the standard form of solution of first order ODE? No, friends, because we have to find the value of k. But now let us interpret this equation. In the equation for I of t, the first part, which is dependent on q, the forcing function, is called as a particular integral or forced response or steady state response. The second part is called as natural response or complementary solution or transient solution. During the next discussion, we shall take up the same simple RL circuit and obtain its solution using classical approach. Friends, consider an example to find the solution for the system response, that is current I in the circuit, for t greater than or equal to 0 in the circuit shown in figure. The switch K is closed at t is equal to 0. We have already obtained the system equation for this circuit, and that is di by dt plus R by L into I is equal to V by L. If we represent this equation in the standard form of ODE, we get di by dt plus P into I is equal to Q, where P is equal to R by L and Q is equal to V by L. We know that the solution for this first order ODE is I of t is equal to e to the power of minus pt into q into integration e to the power of pt into dt plus k into e to the power of minus pt. By substituting the values of p and q in the equation, we get I of t is equal to e to the power of minus r by l into t into v by l into integration e to the power of r by l into t into dt plus k into e to the power of minus r by l into t. Using the simple integration rule, we get I of t is equal to v by r plus k into e to the power of minus r by l into t. Let it be equation 5. We know that k is the initial condition. Hence, using the knowledge of electrical engineering, we have to find I of 0. What is I of 0? It is the current in the circuit or through the inductance before the switch K is closed. What is the time before the switch K is closed? Let it be T0 minus. Do you know why we do this? Because inductance is an energy storing element. So, there is likely that there could be an initial current through it. To find I0, consider the circuit before the switch is closed at t is equal to 0. What is the status of the switch before t is equal to 0 or t is equal to 0 minus? Friends, it is open, we know. So, when the switch K is open, the voltage V is not applied and K is open for a long time. Hence, at t is equal to 0 minus, current in the circuit I0 minus is equal to 0. If the switch K is closed at t is equal to 0, of course the voltage is applied to the circuit. But at t is equal to 0 minus, that is just before the switch is closed, I0 minus is 0. And we know that the inductance opposes the change in current. What does this mean? It means that I0 minus is equal to I0 plus. So, I0 plus or I of 0 is equal to 0. By substituting I of 0 is equal to 0 at t is equal to 0 in the equation 5, we get k is equal to minus v by r. By substituting the value of k in the equation 5, we get I of t is equal to v by r minus v by r into e to the power of minus r by l into t. Friends, this is called as the complete solution for I of t. Is it not simple? Friends, let me summarize about what we have learned in this tutorial. we defined the transient as a transit state between one steady state to another steady state. We also learned that transient state is a temporary state, it vanishes with time, it produces non-periodic variations, and the amplitude of variations will be many times more than those in the steady state. Transients may cause damage also, but transients are unavoidable. They are desirable in electronic systems and they are controlled, whereas they are wholly not desirable in large power system networks. We also realized that the study of the transient analysis is as important as the study of steady state analysis. For both steady state and transient analysis, the knowledge of formation and the solution of differential equations is essential. Both Fourier and Laplace transform approaches require deeper mathematical knowledge and both are labor intensive, whereas classical approach requires only basic knowledge of differentiation and integration. Of course, basic knowledge of finding initial current through the inductance and voltage across the capacitance before switching is required. But using the knowledge domain of basic circuits and behavior of network elements comes in handy to reach the solution of differential equation in most simpler way. Friends, I am sure you have enjoyed this tutorial and understood clearly the concept of transients. Friends, in this tutorial, only a representative example is solved by using classical approach. The major emphasis here was to drive the concept of transient and introduce the classical approach. Friends, during the next tutorial, we shall take up a number of different circuits and find their transient response using classical approach. If this tutorial has ignited some of your thoughts, please forward your feedback and suggestions to my email. Thank you for watching this video.